Next up is Philippe Block. We just recently also met in Zurich. We were visiting them and Philippe's group with my students from Karlsruhe. So Philippe is a professor at the Institute of Technology and Architecture at the ETH in Zurich, where he directs the Block Research Group. He's also director of the Swiss National Center for Competence in Research, NCCR, and Digital Fabrication, which most of you might know. And he's the founding partner of the engineering practice Ochsendorf de Jong and Block. And in the context of the symposium, I think Philippe's work incorporates additive fabrication on multiple scales, which is quite interesting. So masonry shells made from either big blocks of stones or classical bricks. But for example, also the Venice projects brings additive together on two levels. One is kind of a macro scale masonry, and the other one is then also using additive in the fabrication of these components, which I think is really relevant and interesting. Other works that you might have seen involve 3D printing of a formwork for articulated ceiling components. And that also already brings up one of the larger topics they're working on is computational form finding, optimization, and construction, specializing in unreinforced vault structures. So form finding and using geometry to save material. And I'm curious to see what Philippe has to present today. Thank you for joining us today.
Thanks, Moritz. Thanks for the nice introduction. Thanks, everyone, for the invitation. Today, I will specifically, just a second, I will specifically present Striatus, the project we just, that was just in Venice, because I assume that maybe brings together a few of our of the concepts that you just mentioned. So Striatus is a 3D concrete printed masonry bridge, and in the next 15-20 minutes you will hear about it. I'm starting with this little video done by Corporate Communications because I think it nicely summarizes some key things that we try to achieve. So masonry. If, okay, someone else is talking, it seems. Angelo Figliola, could you please mute yourself? Yeah, thanks. All right, so it was a nice collaborative project. As you saw in the text, my research group together with the computational design group at Additive Architects, and then the digital craftsmanship, the beautiful 3D printing, impressive 3D printing was done by Incremental 3D. And then the material developments were done, and also the support of the project was came from Holcim. So you saw already a few things. As said, I call it masonry bridge because it's fully unreinforced. That gives us all kinds of outlooks for end-of-life strategies, which I will emphasize again. And here you see some kind of videos of indeed it then coming together very cleanly, very quickly as a masonry structure. And so these are kind of the key kind of statements, but my talk today will indeed be discussing this interface or the compatibility of masonry logics on multiple levels together with additive manufacturing indeed, particularly in unreinforced concrete. So, but to set the stage a bit, as you know, I'm not necessarily someone that believes that everything will be done in 3D printing in the future, but I I wanted to use this technology en vogue to kind of make a statement and to clarify perhaps that the things that we have been trying to demonstrate for many, many years also apply to this technology. What I'm talking about are two concepts: strength through geometry and material effectiveness. So that is the background. Those of you who know my work and know my history know that I actually started by assessing historic structures in vaulted masonry. But what I find important there is that these historic techniques allowed to basically activate geometry rather than adding material, higher strength materials, reinforcement, and so on. And so this we already We demonstrated this in many different ways, but in the 2016 Venice Biennale with this unreinforced, no glue, no mortar, no reinforcement stone vault, we try to kind of clarify that. And I think now after so many years, I think with striatus, we're managing to basically bring these things together. So what we there already wanted to show or kind of shake the community was to indeed demonstrate and to fully design and engineer something that works because of its shape. So this 4 centimeters of unreinforced stone is held together because of gravity, because of its good geometry and so on. Another message for me that is important in strength through geometry is that it's not just about reducing volume, because that is only part of the equation, but it's also, it allows you to reduce the stresses significantly. And that is why I bring back this very old project in 2008, Peter Rich Architects with John Oxendorf. I did the engineering for the shells. But this to me was eye-opening. On the right, you see these small packages that the women need to carry to site, and that is because the strength of these tiles is just 2 megapascals, so 10-15 times less than a standard concrete in compression. But if you take one of these bricks, you can just break it in bending. And on the left, if you follow the flow of forces in compression, then this becomes a totally safe, totally structural material, as we used to be able to do and used to do in the past indeed. So this we have done to build, for example, permanent floors in an African context. And I'm very excited that later on today, also that this same kind of principle, that if you get the geometry right, vaulted geometry, that then you can activate low strength. And what is important there is that low strength materials are basically also typically low embodied emissions materials that you can locally source and so on. I'm of course referring to the exciting earthen domes that we will see later on as well. So many people often ask, like, what do you achieve with this? And so we now are developing for the market our floor system. And this is what you get for free if you reintroduce these things. I just sneak in this floor because striatus we have designed from the bottom up to actually feature and to celebrate this specific additive manufacturing technique. So, but a floor there you could kind of relate. And so that is that if you were to apply the same ideas, then you would reduce the amount of concrete by 70% and the amount of steel, if you need a tension tie, by 90%. So, but basically where I was coming from with striatus is that concrete I consider, in a simplistic way, of course, as an artificial stone. A stone is happy in compression. So that is why everything that I've said until now makes sense, because these languages then make sense for additive manufacturing, also unreinforced. So this is striatus. Unfortunately, it's being taken down this week, so you have no more chance to see it live. But in striatus, we use, as Moritz actually nicely introduced, we use masonry on 2 levels. A global discretization, like a Roman arch, kind of discretized or orthogonal to the dominant force flow. But then what is extremely important is to also have this consistency locally on the level of the element, of the voussoir. So basically that your print layers are basically also aligned to the force flow. This is, of course, important to not from the beginning, as I see many other approaches from the beginning are fighting to fight this delamination. So by this natural alignment, this is now solved, right? So here you see some very initial sketches. That is what we set out to do. But now what's exciting about 3D printing is that the voussoirs, the pieces, unlike projects before, don't need to be cast, don't need to be subtractively kind of cut. So of course, that is the beauty of this opportunity that concrete 3D printing offers. And as I already emphasized, we do need that alignment to the force flow. So we will be using not the more common extrusion, horizontal kind of 3D printing, but a 2-component 3D printing that allows us indeed to have that control of non-uniform and inclined printing. the real reason why we did striatus is because Shajay Bhushan, the head of the computational design group at Additive Architects, really needs to wrap up his PhD with us, or wants to also wrap up his PhD with us finally. And this is a demonstration, final demonstration of his research. And what is key and why I want to pause here a little bit is that we don't design something that we think makes sense and then start to slice it. But basically what we do is we make the print path explicit and the geometry implicit. So that means that in the print path, we encode already all the global and local structural constraints. We encode already the fabrication limits that we discover through targeted prototyping. And so that means that basically it allows us to anything that we print. I get these questions sometimes like, what was the failure rate? Well, 0. As soon as we set up this design framework, everything we printed was ready, precise, was exactly featuring what we needed to feature. And this is really not an exaggeration. And so actually what was interesting about striatus is that, and I hope this is not too abstract, but that we controlled the global geometry explicitly by the interfaces and by basically the global stereotomic kind of logic. And then locally, we let the print path be what it needed to be. So that is where we basically had an implicit logic. So we went both bottom up and top down at the same time. So again, as said, 3D printing, very important to really be as pure and clear about our message of strength through geometry. So this local alignment, and here you see, for example, these bifurcating pieces. You see that we go from one plane to 2 planes. And so it's not just about morphing in 3D, it's really, there is a bit more there. Because I'm talking to experts, I thought maybe of showing one little insight of some of also the iterations that were done with the fabrication. For example, if you were to squirt one of these layers, then you see that we have about 2.5 centimeters. But that was not sufficient for the point loads of people walking on top and so on. So we needed to double up. And so initial tests then look like this. And you see this very dominant, prominent kind of scene in the middle, because at a certain point, you need to turn around because for sake of efficiency, okay, we have a stop and go kind of mechanism, but you want to keep going in order to kind of make the fabrication realistic and relevant. But this was deemed as kind of a bit too much in your face, not that elegant and so on. So rather than admitting, then in the design pipeline, we actually saw this as a design feature, as an opportunity. And so here you see that basically instead of doing one big turn, this turn was done at every internal kind of bracing. And that also gave us an opportunity to, from the outside, to not only give an additional structural expression, but also to actually give a hint how the structure was built. And you see basically these features appear. For the balustrade arches, which are also entirely unreinforced, we used another technique. So here you see in the middle, you see basically that there was this sort of zippering logic in turning around, right? So this is another strategy. But then again, maybe here, you see that each time you turn the corner, you will kind of indent that last layer a little bit. And so this also was noticed during this fabrication kind of prototyping and tests. And so this then accident or feature was then coherently kind of controlled over the entire structure, so that indeed it became again a beautiful aesthetic feature. So, but oh, this 84 hours appeared a bit too early, so apologies for that. But so again, 3D printing, this two-component 3D printing allowed us to be very precise about the force-aligned kind of layers, but also, as you see on the left, to have significant advantages compared to casting, compared to subtractive. Of course, all of you know this by optimizing the internal as well without the need of molds. So in that sense, I think it's a beautiful coming together of historic principles with really the opportunities of a new fabrication technique to be even more extreme than we managed to be in any of our previous projects indeed. So why the 84 hours is because all the pieces, all 53 pieces, including pre and post processing printing, processing of the printing took 84 hours in total to print a bridge. So this is super exciting. This is, of course, an additional advantage that we can talk about different, totally different kind of timings and roles between the development and then the actual fabrication, totally different kind of productivity opportunities and. So because also this hollowing out, as very obvious to all of you, we ended up with a very light construction that could be assembled just with 2 professionals and then 2 people, and then Tom and Alessandro from our team. So we did the entire project management and also on-site kind of strategy. But of course, we needed some professionals there to cover our asses when anything would have gone wrong, which luckily it didn't. Well, that's not true. Some of the blocks fell off the boat were broken, had to be reprinted. That caused all kind of tolerance and anyway. So it's not true that nothing went wrong, but anyway, nothing fundamentally went wrong. But here again, kind of nicely showing these hollow bricks coming together. So, but why I am excited about what we did here is not just the object. After this, I will just take a few minutes to celebrate. I'm proud of how it looks. I think we achieved a very coherent, beautiful kind of thing. But these 4 things for me are perhaps more important. We indeed place material where it really wants to be. This artificial stone wants to be in compression. We need the structural depth, but we don't need the full mass. That is where the hollow infills and so on make a lot of sense. So we really reduce. Repair is a powerful thing in a circular economy thinking, is that by a very disciplined separation of materials, we have a very clear maintenance strategy, which for infrastructure, I mean, I'm not suggesting that this is already an infrastructural piece, but for infrastructure, this would be quite an important argument because we assemble it dry assembled without connections, without chemical connections, so without glues, without mortars. It gives us a very easy reversibility and demountability, and so it can be taken apart. Maybe again, for a bridge, you might say, why do you need to move your bridge around? That is not relevant. And you could also say, this is the most stupid bridge ever because it's spanning over nothing. Also true end to end. But what I wanted to say, this reuse, this dry assembly of elements might really be a powerful concept indeed for prefabrication, prefabricated components in general, which we are also doing, for example, for our floor. And then lastly, again, because of this discipline of separating materials, so we are talking about a truly unreinforced concrete system. We have low energy, super easy recycling opportunities at the end of the lifetime. So these are the bigger picture things that I wanted to show with this bridge. But as promised, here a little bit of a celebration of something. I hope that some of you could see this in person. It will after this week no longer be there. Some of the features here on the left that I talked about that we could then really express and celebrate to both give this flow of forces an aesthetic, but also actually to give a hint indeed on how this was built. Here on the side in the main arch, you see these small shadow joints appear. That is indeed this indentation that gives a hint of what happens on the inside and. Yeah, so unfortunately, this week it's being taken down. That begs the question, why? Where is it going? Well, we pushed a lot of things in parallel. Like, for example, there is 4 rather distinct mixes that were developed on the fly because we learned a lot of things while printing in this bridge and so on. There's a lot of long-term questions on these kind of materials and structures and so on. So we now made a nice deal with Holcim that we are reprinting it in 100% clinker-free 3D printing ink. So practically no more embodied emissions. And we will do this on their innovation center in Lyon, which allows us to do long-term monitoring to really understand the behavior of this structure end to end. So I'm excited to show you this, hopefully in a couple of months or a year from now, that we managed actually to address. The only non-consistent thing is that we, of course, used a totally overkill material to realize this structure. So as I said, a beautiful collaboration between our research group at ETH, the block research group, and then the computational design group at Additive Architects. Of course, it's highly convenient that the head of that group is also our PhD student. So I love this kind of collaboration where you can boss the other partners around. And then incremental 3D, long-term partnerships. So this is not, we just went to a random printing. We have been collaborating with them for years. We have been calibrating our pipelines for years. And so that indeed, when we cranked this out in barely over 5 months, that we basically were ready to go. We were ready to go because from the beginning, as I said, very consistently, the framework, the design framework was agreed upon. We did this coordination through Compass. And more specifically, also what's interesting there is that from the beginning, we defined all the interfaces between all partners. So that meant that 3, actually 4 in parallel developments could happen. And we always exchange kind of learning. So the design framework was being developed, the engineering understanding and framework was being developed, the material development was being developed, and then also all the 3D printing, because a totally new setup had to be developed from the beginning. So this was done very coherently from the beginning. I want to end actually with those statements because I believe that is also what's needed. If we bring our innovations isolated into real projects, then we will never manage to really capitalize on all the things that really matter, on elegantly introduce it, on being economical about it as well, and so on. So that is why I wanted to finish with also emphasizing that this would not have happened without that kind of computational approach. But more importantly, also with that respect and that understanding and trust also that we could develop all at the same time and then deliver exactly when it mattered. So with that, I spoke for exactly 20 minutes. Thanks again for the invitation, and I look forward to the discussion later.
Great.
Yes, perfect. Perfect timing. Really interesting contact. Thank you, Philippe. I think the idea was to have, Uli, correct me if I'm wrong, to have like 2-3 minutes per talk discussion, right?
Yeah.
Yeah.
Give it 2-3 minutes and then we go to the next.
Okay, perfect. Very good. Yeah, I love the outlook of this. One question that I would have looking at the images is the form work. Yeah? Can there be an interesting, let's say, if we have all those opportunities of additive and articulation of those components, can there be an installation procedure be integrated, or like a moldless installation procedure being integrated into a more, let's say, intelligent joinery for the process? And then talking about functional integration, which other opportunities do you see to use those hollow spaces inside for other functions? Because you're taking material away, that gives us space for other things, right?
Yeah, so great, thanks. Indeed, that would be the next step. I mean, forgive us that we had to be a bit pragmatic, we were running out of time. And I do believe indeed that the key thing that we didn't demonstrate properly or at all, or addressed at all, is actually the challenge of logistics indeed. And so not just the assembly, but also picking up the pieces, installing it carefully, and not kind of having to over design for transport, for logistics, for lifting in and so on. So, but I don't see a fundamental kind of challenge there, because as soon as people are convinced that this might be a good approach, then formwork people or researchers will figure out some reusable, flexible kind of things to support these things, right? So I think that to me is kind of not that important. I do want to make a quick comment about your question about functional integration. To use the cavities that exist and to make them actually also accessible and so on, yes, good idea. Functional integration, I would question that, because I really believe that one of the most effective ways of actually being circular is to extend the lifetime of things. So I'm very skeptical of locking in specific functions, specific kind of integration of systems and so on, together with a structural component, because that will kind of also lock in unquestionably in 10, 20 years, the systems will be better. We need to update another user and. So I am very skeptical of a functional integration in that very extreme way. I would say we want to integrate, use these opportunities, but we have to have the same discipline of the outlook of end of life, of future reuse, of adaptability, and so on. Yeah.
That's a super interesting point. I'm going to take that for the discussion later, because say this functional integration doesn't per se mean that you somehow need to integrate pipes or things like this. But say the structural performance is already something which is integrated. You may also think about building physics as performance aspects, which will not change due to the material. But that's something which we really should discuss in the next setup. Super interesting. And Philippe, I had the chance to see this, and it was a super nice project. Thanks for really developing it. I really get the story and really get the outline. Let's move to the next. Chris, it's your turn to introduce the next speaker.
May I interrupt you? Philippe raised his hand and would like a question. Maybe
okay.
For that one.
Good. Give this one question and then we go, because we need to have a discussion after the block.
Okay. Thank you for the awesome presentation, Philippe. Actually, I have two questions, so I will choose one. I have a very specific one and probably a simple and naive one. So I'll choose the simple one, which is, why do you think did we kind of, so to speak, forget these funicular strategies? Because you mentioned that they were used in history like a long time ago.
Yeah.
Now we are coming back and they are providing a lot of advantages. And why do you think?
Well, thanks for the question, and I think it's a perfect question for this audience. I think it's you see innovation happen when there is a crisis, when it's really needed. Like, for example, Pierluigi Nervi could build his Palazzetto dello Sport because at the time steel was very expensive and it had to be an efficient structure with least amount of, and mainly unreinforced concrete rather than the typical kind of materials that were not possible then in the 50s in Italy. Sorry, my office mate decided to make a coffee. Sorry, I lost my train of thought. No, so here as well. So now we do have two things that happen at the same time. We have extreme pressures of climate change, right? Of really taking our responsibility. And we have indeed digital fabrication, more specifically additive manufacturing, that is scaling up to be mature and ready for construction scale applications. So that means that the reason to do it is there, but also now we can do this in a realistic and economical kind of way. And so, because these geometries are non-standard, 2-3 years ago, it was really a challenge. It was not obvious to actually realize this non-standard. Now we are at a point that we can do that. So I think it's exactly the right moment. We have to do it, and we can now do it. So this is very exciting.